In this section, we are going to work on, again, optimization, just like we were doing in chapter 5, where we were finding maxes and mins of linear equations. Now we're going to find maxes and mins of things that are not linear. But before we get there, I want to do a quick little review of how would you do this using regular calculus. How would you do this back from your previous brief calculus course? So highly recommend. Try it yourself. See if it comes back. Find the min or max of this equation using first and second derivatives. No graphing is allowed. You cannot use your graphing calculator because when we go forward here, when we're graphing in 3D, you're not going to be doing that, and you're definitely not going to be sketching graphs by hand. So you got to get the big idea. Okay, pause the video, give it a shot. All right. So as a quick reminder, we take a first derivative, right? So we take the first derivative, that's going to give us 6x minus 4. Now, what does this mean to me? Well, and how is it useful in finding a max or a min? Well, just as a quick sketch of this graph, I know you're not allowed to use a graphing, but it's just to help us get a visual. This is a parabola opening up, right? Now, where it goes, I don't know, and I don't really care. The idea we're going to see is we're going to have a parabola, it's opening up, which means we therefore have a min. Now, what I want you to keep in mind now is, what is a derivative? What does a derivative mean? Well, it's slope of the tangent line. And if I want to find the max or a min, then I know the slope of the tangent line is 0. So what I do is I take my first derivative, I set it equal to 0, and now I solve. So therefore I add 4, divide by 6, so that's going to give me x is 2/3. So therefore I know that this value is at 2/3. But am I done? No. To talk about a max or a min, to talk about its optimal optimization, I need to have the y value as well. So where do I go? Do I take that and substitute it back into the derivative? No, that wouldn't make sense because I want a y value. And this is not y values, this is slope. So therefore, I have to take this 2/3 and substitute it back into the original problem. I'm going to pause the video while I do that. Okay, so I substituted that into my calculator and I got 17/3. Great, there's my value. Now, if I didn't have the graph, could we have done everything up to this point? Absolutely. We had just said, okay, derivative set equal to 0. That's going to give me my list of mins or maxes. So therefore, I solve, I get my x value, take that, sub it back in, get my y value. But now I need to figure out, what is it? Is it a min or a max? Well, and clearly you got my hint in the direction. We're going to need a second derivative for something. So the second derivative of this is 6. Now remember, what do second derivatives talk about? Well, these are concavity, right? These are concavity. And so if it's a positive number, it means your graph is concave up. If it's a negative number, it means your graph is concave down. So since it's positive, it's concave up. When I have concave up graphs, and I know it's a 0 there, whoops, I know it has a slope of tangent line 0, I know it is a min. So positive second derivative means it's a min, so therefore I know, therefore this point is a minimum. That's the big idea. First derivatives tell you your location. Second derivatives tell you your max or min, concavity up, concave down. Okay, so now we're going to move on. That was a little review. Now we're going to move on to what we can do in 3D. So before we get started, what I want you to do is go to our website for the 3D graphing tool. I put it here again. It's from the 15.1 notes, same thing. Or you can use any 3D graphing tool. It doesn't have to be this one. But I want to graph this equation. So let's go ahead and type that in. I'm going to pause the video while I bring that. Okay. So I went ahead and typed in the equation into the line here, and I hit enter, and this is what it gives us. Now, if you scroll out a little bit, it makes it a little easier to see. I'm doing this by pressing the control key and the wheel on my mouse. I'm bringing it down. You can do it in your browser however you want. Even if you can't figure out how to do that, you can always just turn the graph to kind of see what we want to see. Now, we have our graph. The key things I want to talk about now. I'm going to move this off the screen for a second. You have your graph, you're kind of looking at it. What we're going to talk about is, what does a minimum or a maximum look like in 3D? Okay, well, it's kind of easy to visualize. Oh, actually, you don't even have to press the control, just the wheelie does it. Okay, so what does a max look like in the real world? Well, it kind of looks like the top of a mountain. So do you see we'd have a maximum right here? And the key to this is a maximum should be a maximum all around. So no matter how you rotate it, I should use the keyboard for this. There we go. So no matter how we rotate it, do you see it looks like the top of a hill? Now, obviously, we're getting blocked by another part here, but you have the top of the hill right here, right? And no matter how we rotate around, it's always the top. So that is a max. Now, does this graph have a minimum? Well, let me zoom out just a tiny smidge. And when we zoom out, we see it gets a different kind of different look here. But what would a minimum look like in 3D? So if I flip around to the backside, we show the backside. Do you see down here, kind of hanging down, right here? You have a kind of like, if you imagine pouring water into it, it would hold water. It's a lake. That would be a minimum. That's a low point for that area. So this graph has both a maximum and a minimum. So that is two of our checklists. That's two of our important parts for what we're doing in our notes. We want a maximum. What does it look like? Well, it just looks like a hill. What does a minimum look like? Well, it would be a lake if it was filled with water. It looks like a valley. Saddle points. This is a new kind of thing. This is something new. And what a saddle point is it is a max in one direction and a min in the other. Okay? Min in the other. So when we go back and look at our graph, do you see the saddle point? Think about it as like a saddle, like literally, if you were riding a horse, your legs would hang over here and to the other side, and then your body, your torso would go up in this white space, and you'd hold on to the little handle right here, and then there's my head. Wow, my head is really small. But nonetheless, and my ears are now going to be huge. Anyway, whatever. So the idea, it's a saddle. And so what the key idea to this is it's a maximum one direction, minimum in the other. And to make sure we see it, I want to just point out that the maximum, you can see this part is a maximum because the graph would be angled kind of like this. So it'd have a maximum. It's just hanging up and over where your legs are. And then the other side, oh, it does work. Then the other side would be a minimum because we would be tracing right here inside. So we'd be coming up in here. So you can see that part of the graph is angling like a minimum for a graph. So there's how you have a max and a min in two different directions. One would be in the x direction, one would be in the y direction. Not terribly important which one is which, just that one, you have one of each. All right, you got that? You got the big idea. So now, that is the theory. So now we're going to do the how do you calculate this? How do I actually find them? And that's what we'll do in the next video. We're going to take the same equation and we're actually going to find these answers.